Today, the topic of discussion is on basic concept of refrigeration and air conditioning, that is Module 2, Part 2, PEME 601B. Myself, Dr. Suman Das, HOD, Department of Mechanical Engineering, Swami Vivekananda Institute of Science and Technology. So in this chapter, we will discuss simple vapor compression refrigeration system, that is VCRS, vapor compression cycle, PHTS diagram, cycle with subcooling, superheating, their effects, effect of changes in evaporator pressure and condenser pressure on the performance of a simple vapor compression refrigeration system, dry compression, wet compression of the refrigerant, actual vapor compression cycle. Now, use of TS and pH chart. So these are the chart. So this is the temperature entropy, this is the pressure enthalpy, and this is also the pressure enthalpy. This is the pressure enthalpy chart. If you see that this is this zone, so this is a superheated zone, and this line is the saturated liquid line, and this is saturated vapor line. Saturated liquid line and saturated vapor line intersect at a point that is called the critical point, and this zone is the superheated region that is mentioned here, and in between saturated liquid line and saturated vapor line, this is the evaporation zone, that is the mixture of liquid and vapor, and this region is the subcooled region, that is the liquid region, subcooled region, and this is the superheated region already I have mentioned. Now state point 1, this is state point 1, 1 to 2, that is the compression part, and 2 to 3 condensation part, 3 to 4, that is the throttling or that is the sudden expansion, and 4 to 1, that is the evaporation. So if you see this diagram, that is the pressure enthalpy diagram, that is the pressure and specific enthalpy denoted by the small p and the h, small h, and this is the 1 to 2 compression, and this is the superheated region, and this one is the constant temperature line. If you see the constant temperature line in this pH chart, pH diagram, say the constant temperature line is looks like this, and this is T2 constant, this is the also the T3 constant, and this is the T4 constant, and this is the constant dryness fraction line. This is here the dryness fraction is H4, sorry, X4, and this is H1 minus H4, that is called refrigerating effect, that is the QA. Okay. Now if you see this diagram, so this diagram there are different lines, different dashed lines. The different dashed lines are representing here. So from this diagram it will be clear that this is the superheated region, and this dash is, that is the constant entropy line, that is the small dash, and this is the constant temperature line. So this line is the constant temperature line, already I have mentioned here. The constant temperature line is this, and this is the constant volume. So this dash dash dash, this is the constant volume. Now problem 3, we will discuss this problem. So this is the problem, this is the refrigerating plant using carbon dioxide as refrigerant, works between 25 degree centigrade and minus 5 degree centigrade. The dryness fraction of carbon dioxide is 0.6, that means 60%. At the entry of the compressor, level, on entry of the compressor, the value of the dryness fraction is 60%. Find the ice formed per day if the relative efficiency is 50%. Ice is formed at 0 degree centigrade from water at 10 degree centigrade. The quantity of carbon dioxide circulated is 6 kg per minute. For water, Cp equals to 4.187 kilojoule per kg. Here L equals to latent heat of fission of ice, that is 335 kilojoule per kg. Now this is the chart, this is the properties of carbon dioxide, that is at the particular temperature 25 degree and minus 5 degree, that is the HF equals to kilojoule per kg, and HFG, that is kilojoule per kg. These values are tabulated in this chart. So now we'll go for the problem discussion. In the TS cycle, if you see that this is the TS diagram. From this TS diagram, the 1 to 2 and 2 to 3 and 3 to 4 and 4 to 1. So this is the cyclic process, and the value of T1 is 273 minus 5. So from that table or from the problem, so this value is given, and similarly the T2 value is also given, that is 273 plus 25, it is in terms of Kelvin. And H1, that is the enthalpy at state point 1, if you see that HF1 plus X into HFG1, so that is directly from the formula. You can directly put the value of HF1, and the dryness fraction is 60% already mentioned in the problem, and HFG1, that is 245.8. So H1 can be easily calculated with the help of this formula, that is 140 kilojoule per kg. Now from this chart, it is clear that S1 equals to S2, so that is the entropy is same. So from the formula we can directly calculate the value of, so is just putting this value, and so this is the final equation, that is S1, the formula is this, and this is the value of S2 formula. Now the work done, this is the x2, that is 0.63, that is the dryness fraction, and h2 equals to hf2, that is x2 hfg2. So this is the value, and w12 equals to h2 minus h1, and we can put the difference of h2 minus h1, we can get the value 70 kilojoule per kg. Now, refrigerating effect. All of you know that refrigerating effect is nothing but the difference of the two enthalpy, that is state point enthalpy at state point 1 and enthalpy at state point 4. So H1 minus H4, that is H1 minus H1 minus H4 equals to H3. So we can put the H3 value instead of H4, and finally H1 minus HF3. Okay, so this is the COP is nothing but QA minus W12. So putting this value QA, and that is the W12 equals to this, and we can get the value of CP. Now the actual the work done per second, that is the work done per second, and actual cooling effect. So 1.725 into 1.7, that is the work done per second. So we are getting this value. Now, heat carried to form 1 kg of ice, that is Cp into T2 minus T1 plus L. So this is the value of the heat carried to form 1 kg of ice. And ice formed per hour. So this is the ice formed per hour. Just with the formula, we just put this value, and we are getting the value of ice formed per hour. Now next problem. A refrigerator operating on a standard vapor compression cycle has a coefficient of performance of 6.5 and is driven by 50 kilowatt compressor. The enthalpies of saturated liquid and saturated vapor refrigerant at the operating condensing temperature 35 degree and 35 degrees centigrade are 69.55 kilojoule per kg and 201.45 kilojoule per kg respectively. The saturated refrigerant vapor leaving the evaporator has an enthalpy of 187.53 kilojoule per kg. Okay. Find the refrigerant temperature at the compressor discharge, that we have to calculate. The Cp of the refrigerant vapor may be taken as to be 0.6115 kilojoule per kg Kelvin. Now the solution. Cp, that is coefficient of performance, that is 6.5. So compressor power is 50 kilowatt. So refrigerating capacity. So just by multiplying with these two, you can get the value of 325 kilowatt. Heat extracted per kg of refrigerant. So that will be the difference of the two, and we are getting this value. Now the refrigerant rate, that is mass flow rate, that is 325. 325, that is refrigerating capacity divided by heat rejected per kg of refrigerant. So if we just divide these two, and we are getting that is the kilojoule per second. So heat input, that is also, that is the 50, that is the compressor power divided by 2.57, that is the refrigerant rate. So this is the heat input. Now enthalpy of vapor after compression, so that is the sum of these two, and we are getting this value. So in the case of superheat, so we are getting this value, so degree of superheat, so finally we are getting this value. Now the temperature of refrigerant at compressor discharge, that is 35 plus 6.687, that is 41.87 degrees centigrade. Now the problem number 5, a refrigeration system of 15-ton capacity operates an standard simple vapor compression cycle using the refrigerant minus 22 to an evaporator temperature of 5 degrees centigrade and condensing temperature 50 degrees centigrade. Draw pH diagram from the cycle. Calculate A, the refrigerant mass flow rate, B, the compressor intake, volume flow rate, if the compressor volume efficiency 70.72, is refrigerant property data given in the table below. So this is the data in the table, that is at temperature 5 and 50 degrees centigrade, the pressure is this, and the corresponding enthalpies, corresponding specific volume. Okay, so these are given in the problem. So if you see that this is the compressor 1 to 2 part, after that 2 to 3, 3 to 4, and 4 to 1. This is a cyclic process, 1 to 2, and this is the compressor discharge temperature, that is 50 degrees centigrade, and this is the 4 to 1, that is evaporator, that is maintained at 5 degrees centigrade. So refer to the figure, that is the solution. And this is the capacity of the plant. Capacity of the plant is nothing but mass flow rate into H1 minus H4 by 3.517. So we are getting the value of H1. We know the value of H1 and H4. So finally the M dot can be easily be calculated. That is the mass flow rate. So volume flow rate, that is the M dot into M into Vg by the NC, that is the efficiency. So we are getting this value. Now problem number 6. So this is a refrigeration cycle used freon minus 12, freon 12 as a working fluid. The temperature of the refrigerant in the evaporator is minus 10 degrees centigrade. The condensing temperature 40 degrees centigrade. The cooling load is that is 150 watt, and the volumetric efficiency of the compressor is 80%. The speed of the compressor is 720 rpm. Calculate the mass flow rate of the refrigerant and the displacement volume of the compressor. So this is the property of freon 12, that is the temperature, corresponding saturation pressure, enthalpy, and specific volume. So this is the solution. So this is the cooling load, that is Q is given 150. So H1 minus H4, that is refrigerating effect, all of you know, that is H1 minus H4, that is enthalpy difference 183 minus 74, that is directly we are getting from this value from the table, from the chart. So finally this, and this is refrigerating effect, that is multiplied by mass flow rate, that is the value of Q. So mass flow rate is nothing but m dot equals to 150, that is the cooling load, in terms of watt, divided by 108.5 into the power 3, that is the value of mass flow rate is 0.001382 kg per second. Displacement of the compressor, that is nothing but capital V1 equals to m dot, that is mass flow rate into specific volume divided by efficiency. So ultimately we are getting this value 1.382 into 10 to the power minus 4 meter cube per second. Thank you.